Welcome to another Deep Dive, your go-to resource for becoming truly well-informed on the most crucial topics shaping our world. Today, we're plunging into a rapidly evolving and uh, absolutely critical area, the operational landscape of artificial intelligence. Specifically, we're zeroing in on the unique threats and vulnerabilities that these powerful systems face. And perhaps even more importantly, how we can effectively control and, mitigate those risks.
That's right. As AI becomes more deeply integrated into, well, pretty much every facet of our lives, from the algorithm suggesting your next show to complex systems managing critical infrastructure, understanding its unique risk factors and how to manage them is absolutely paramount.
Right.
We're moving beyond just applying general cybersecurity principles here. We're grappling with a fundamentally new class of challenges, challenges that arise directly from the very nature of AI's learning, its decision-making, and often its inherent complexity.
Absolutely. So, our mission for this deep dive is pretty precise and practical too. We're going to unpack Chapter 2, Part F of the ISACA Advanced in AI Audit Official Review Manual. This section is dedicated to threats and vulnerabilities specific to AI and, crucially, the corresponding controls designed to counteract them. Think of us as your expert guides, navigating you through this complex but incredibly fascinating subject. We'll go topic by topic, just as instructors would in like a focused masterclass.
And it's really crucial to understand where this information comes from, the source material, I mean. This manual is a foundational review resource specifically tailored for AI audit professionals. So what we're discussing today isn't just theoretical. Its insights are directly applicable and critical for anyone who is working with or developing or auditing or even just relying on AI systems in real-world high-stakes environments. It's about practical, actionable knowledge.
Okay, let's unpack this then. Let's jump right into the first main section, setting the stage by looking at the broader, evolving landscape of AI threats. It's almost a given, isn't it? Whenever groundbreaking new technologies emerge, they inevitably bring along entirely new attack vectors. For artificial intelligence, this isn't just about finding traditional software bugs or, network vulnerabilities. It's about uncovering unique and often quite insidious ways malicious actors can exploit the very learning and decision-making processes of the AI itself. This is a completely different playing field, demanding a fresh perspective on security.
Precisely. And what's truly fascinating here is how quickly these attacks have evolved, particularly with the advent and, well, the widespread adoption of generative AI or Gen AI models. Attackers aren't just looking for typical system weaknesses anymore. We're seeing incredibly novel methods emerge. Things like subtle modulations of interaction, which might involve tiny, almost imperceptible changes in how a user interacts with an AI that subtly nudges towards undesirable behavior, sort of bypassing overt safeguards.
Subtle nudges.
Yeah. We also see clever test prompts specifically designed to trick large language models into revealing sensitive info or generating harmful content that they've actually been programmed to avoid. And perhaps even more concerning are sophisticated data input and instruction substitution attacks.
Yeah, what does that involve exactly?
Well, that's where the very information fed to the AI or the instructions it's given are subtly swapped out for malicious content, basically leading it down a path of compromise. The attack surface isn't confined to the code or the network anymore. It's dynamically shifting to the data itself and the complex interaction patterns with the AI.
That's a fundamental shift in how we even conceive of digital threats. Wow. So to help us understand and categorize these rapidly evolving attack types, a crucial framework has emerged. It's the MIT ATT&CK for Artificial Intelligence Systems, or ATS. Many of you listening might be familiar with the original MIT AT&CK framework for traditional cybersecurity, but this is its AI-specific counterpart. It's described as a comprehensive knowledge base of adversarial tactics and techniques, something that AI red teams, those security pros who simulate attacks to find weaknesses, can leverage. So for you, the listener, why is it so important to be aware of a framework like ATS? What's the tangible benefit here?
ATLAS is indispensable, really. It provides a structured, almost encyclopedic way to think about AI security. Instead of approaching AI threats as, just a series of isolated incidents, ATLAS helps us move beyond generic IT threats. It helps us focus on specific, categorized AI attack scenarios. It meticulously outlines the various stages an adversary might go through, from initial reconnaissance and resource development like building their own poison data sets, all the way to execution, persistence, and impact.
So it maps out the whole life cycle of an AI attack.
Exactly. This structured approach helps categorize and understand the how of these attacks, the actual technical steps and methods employed. And that's absolutely crucial for building robust, proactive defenses. It's like having a comprehensive playbook of all the known adversarial moves, allowing defenders to anticipate and counter them systematically.
Having that detailed playbook is invaluable for any organization developing or deploying AI, definitely. And building on that, another significant resource is the OWASP AI Exchange. It takes a slightly different approach, I think,
Yeah.
classifying general AI security threats into three major attack surfaces. This gives us an even clearer roadmap for our deep dive into the specific threat types outlined in the ISI manual, ensuring we cover the full spectrum of vulnerabilities from, well, different conceptual angles. All right, now that we've set the stage with the broader threat landscape and these key frameworks, let's jump into the first major category. The first category of threats that the source identifies: development time threats. What exactly does that term mean? And why is this particular phase so profoundly critical for the overall security and integrity of an AI system?
Development time threats are precisely what their name implies, those that occur during the development of AI systems.
Hmm.
This is a profoundly critical phase because any vulnerabilities or biases or malicious components introduced here can be incredibly difficult, if not impossible, to fix later once the AI is deployed.
Right, it's baked in from the start.
Exactly. The source emphasizes that the primary attack surfaces include the engineering environment and the supply chain of the AI model itself. This means that weaknesses, biases, or even outright malicious code can be inadvertently or intentionally baked into the system from the very beginning, long before it ever interacts with a user or goes live in a production environment. Securing this foundational stage is paramount. A flawed foundation can compromise the entire structure built upon it.
Okay, here's where it gets really interesting, because the source, specifically figure 2.9, breaks down these development time threats. It lists several distinct categories that impact the AI model itself. Let's start by unpacking model supply chain threats.
Right, model supply chain threats. These involve risks from untrustworthy components used in building the AI model. To elaborate a bit, AI development today, well, it rarely starts completely from scratch. It relies heavily on a complex ecosystem of pre-trained models, maybe a large language model fine-tuned for a specific task. It relies on open source libraries, frameworks, datasets from various external sources.
So you're pulling in lots of building blocks from elsewhere.
Precisely. And if any of these components are compromised during their own creation or distribution, if they contain hidden vulnerabilities or have malicious code embedded within them, then your entire AI system, which incorporates them, is immediately at risk. It's a subtle but pervasive threat because even well-intentioned developers could unknowingly integrate compromised elements.
Right. It's like trying to build a high-tech car using a seemingly legitimate but actually faulty engine part sourced from a third party. The flaw is integrated before the car even leaves the factory, making it incredibly hard to detect later on without deep specialized diagnostics. The so what, for you, the listener, is the critical need for rigorous vetting, scanning, and continuous monitoring of all external dependencies in your AI development pipeline. You have to recognize that your AI is only as secure as its weakest link in that supply chain.
Absolutely. Next on the list, we dive into model poisoning. This describes the deliberate act of manipulating the training data with malicious data to degrade the model's performance. But it's not just about making the model less accurate. It can be used to introduce specific, often subtle, biases, or even create backdoors that can be exploited later.
Can you give an example of that?
Sure. Imagine feeding an image recognition AI corrupted images of a specific object. You could train it to always misclassify that object. Or feeding a fraud detection AI subtle patterns that allow certain types of fraudulent transactions to just pass right through, undetected. It's basically like feeding a student incorrect or distorted information during their formative learning phase. It leads them to fundamentally flawed conclusions or pre-programmed errors that are really difficult to correct once ingrained.
That truly highlights the insidious nature of this attack. It's not about outright breaking the model in an obvious way, is it? It's more about quietly corrupting its core knowledge, making it behave in ways it was never intended to, often with long-term, devastating consequences.
That's exactly it.
Imagine an AI system trained to evaluate loan applications. If subtly poisoned, it could develop biases that unfairly discriminate against certain demographics,
Yeah.
or conversely, approve high-risk loans that lead to massive financial losses. It's a very quiet, yet potentially catastrophic form of sabotage because the model appears to be functioning correctly on the surface.
It does. Okay, moving on to model evasion. This involves crafting what are called adversarial examples. These are subtle, carefully crafted inputs, like tiny, almost imperceptible changes to pixels in an image, or characters in text, that are designed to trick the AI model into misclassifying or making incorrect decisions, even if that input appears perfectly normal and harmless to a human observer.
So the AI is evaded by something a human wouldn't even notice.
Pretty much. The model is evaded by inputs it should correctly interpret. What's critical here is that these aren't random errors. They actually exploit the model's blind spots, where small, targeted perturbations in input features push the AI's internal feature detectors into a misclassification. It highlights a key difference between human and AI perception. Robustness to such tiny changes is still an active area of research.
A truly chilling and relatable example here would be that stop sign example. A stop sign with a tiny, nearly invisible sticker placed on it that makes an autonomous vehicle misinterpret it. Maybe it's a speed limit sign or even a blank sign. The visual change is imperceptible to a human eye, but to the AI, it causes a catastrophic misclassification. The implications here for safety-critical AI systems like self-driving cars or medical diagnostic tools are just immense. It shows how even a seemingly perfect AI can be tricked.
It really does. Then there's model inversion. This refers to the process of reverse engineering the model to extract sensitive information. This could be details about the original training data used to build the model, things like facial features, sensitive text passages, proprietary financial records. It could also reveal proprietary model parameters and intellectual property, effectively exposing the secret sauce of the AI. It's about pulling information out of the model that was never intended to be revealed, essentially unmasking what it learned and potentially from whom.
This raises a profoundly important question about data privacy for you, the listener. If a face recognition AI is trained on your personal images, could a malicious actor use model inversion techniques to extract details about those faces, or even reconstruct them or aspects of them from the AI itself? Or if a medical AI is trained on patient records, could private health information be inferred and extracted? That's a serious privacy concern, isn't it? Far beyond just, data leakage from a database.
Absolutely. And closely related is model theft. This is broadly defined as unauthorized access to the model itself, which includes its learned parameters, often called weights, its architecture, or the proprietary algorithms that define its functionality. This isn't just about stealing code. It's a direct attack on the intellectual property and competitive advantage of an organization that has invested heavily in developing that AI.
How does model theft happen?
Well, it can manifest through various means, from gaining direct access to the model's hosting environment to more subtle methods like probing a publicly accessible AI API with carefully crafted queries, to try and reconstruct the model's internal logic bit by bit.
You can frame that as industrial espionage in the AI age, someone stealing your secret recipe for AI success. If your entire business model is built around a proprietary AI, losing that model to a competitor or a malicious actor is akin to losing your entire product line and competitive edge. It's an enormous threat to innovation and business security.
It certainly is. Another significant threat is control flow hijack. This involves exploiting vulnerabilities to force unexpected model behavior. Essentially, an attacker manipulates the AI's internal processing logic, making it execute actions it wasn't programmed or trained to do. Unlike model evasion, which tricks the model's perception, control flow hijack aims to alter its fundamental operational commands.
So it's taking control of what it does, not just how it sees things.
Exactly. This could lead to unpredictable errors, malicious actions, or a complete subversion of the AI's intended purpose. For instance, an AI-powered industrial robot could suddenly move erratically, causing damage or injury. Or a conversational AI could be made to perform an unauthorized financial transaction.
This sounds like the AI going completely off script and doing something arbitrary or perhaps even malicious that is fundamentally outside its design parameters. What are the profound implications for trustworthiness here, especially in critical domains like healthcare or autonomous systems? If an AI can suddenly be coerced into such unpredictable actions, it makes you question the very reliability and safety of the entire system.
It does. And finally, under threats impacting the AI model itself during development, we have output prompt injection. This is a particularly insidious threat because it refers to malicious instructions embedded within the model's output rather than its input.
Wait, in the output, how does that work?
Yeah, these embedded instructions are designed to manipulate downstream systems or users who interact with that output. For example, a generative AI model might be tricked into including a malicious JavaScript payload in a generated code snippet, or a deceptive link within a generated email that then affects the recipient or their system. It's the AI's own generated response carrying the attack payload, essentially weaponizing the AI's creativity.
So to clarify, the AI itself could be coerced into generating a harmful command, a malicious piece of code, or misleading information that then affects other systems or users. That's a significant shift in how we think about AI security. It's not just about guarding the input, but also rigorously vetting the output for embedded threats. The AI becomes an unwitting accomplice.
That's precise.
Now that we've delved deep into the threats directly impacting the AI model itself during development, let's explore other critical areas. The source also identifies threats on inputs during development, still under Figure 2.9. This includes a concept we touched on earlier, but now revisited in this specific context: input data poisoning.
Yes, input data poisoning applies here as well, but the focus in the development context is specifically on manipulating the training data, manipulating it to affect the model's fundamental learning outcomes and its long-term behavior. This goes beyond a single runtime interaction. It's about corrupting the very source of the AI's knowledge, teaching it incorrect associations or biases right from the start.
So before it's even fully trained.
Exactly. An attacker could subtly inject manipulated data into a dataset before training begins. This causes the AI to learn faulty patterns that propagate through its entire operational life. It makes the AI inherently flawed from its inception.
And then, particularly relevant for generative AI, we have input prompt injection, but now we're considering it in a development context, specifically concerning training.
Correct. For Gen AI, this is where malicious input during the training phase directly influences the model's future behavior or outputs. Unlike a one-off runtime attack where a user tries to bypass current safeguards, here the attacker aims to teach the model to inherently produce undesired behaviors, or to ignore safety guidelines in the future regardless of subsequent safeguards put in place later.
How would they do that?
For example, feeding a model prompts during training that contain hidden instructions could train it to always include certain biased phrases, or maybe respond evasively to queries about sensitive topics, making it really difficult to correct later.
So it's truly about poisoning the well of knowledge, right from the very beginning of the AI's existence. The direct and potentially persistent impact on the AI's responses and its adherence to safety guidelines makes this a formidable threat, one you really have to tackle proactively.
Definitely.
Okay, moving to another critical area within development, the manual covers threats on data. These are crucial, especially given the vast datasets involved. Let's start with data leakage.
Data leakage in this context refers to the unintended exposure of sensitive data used throughout the entire AI development lifecycle. And this isn't just about the final training dataset. It encompasses all data handled from collection and preprocessing to model testing. This could be anything from confidential customer information, proprietary algorithms embedded in intermediate datasets, or trade secrets inadvertently exposed during data sharing or storage.
And it's usually accidental.
Right, it's often an accidental but highly damaging release of protected information, often due to misconfigurations or inadequate access controls in the development environment.
And closely related to that, and equally critical, is data privacy violation.
Indeed. Data privacy violation connects directly to data leakage, but it specifically focuses on unauthorized access to personal data within the development environment. This has profound direct legal and ethical implications. Under stringent privacy regulations like GDPR, CCPA, or hate pay, a breach here means not just a loss of data, but a direct infringement on individual privacy rights, leading to significant fines, legal action, and severe reputational damage for the organization responsible.
This raises an important question about the sheer volume of sensitive data that is often handled in the AI development pipeline, from customer demographics to proprietary designs. For you, the listener, understanding these risks, it really highlights the immense challenge in maintaining data security throughout every single stage, and why robust data governance from day one is just non-negotiable.
Absolutely non-negotiable.
The source also details threats on compute, which are equally vital given the immense processing power AI systems demand. First, resource exhaustion.
Resource exhaustion describes a specific type of denial of service attack. It's aimed squarely at the substantial computing resources used for AI development or operation. AI training and complex inference are incredibly compute-intensive, often relying on specialized hardware like GPUs or TPUs. So, overwhelming these resources with malicious activity, like a flood of illegitimate model queries or rogue training jobs, can render the AI system unavailable or severely degraded, effectively taking it offline. This can halt critical development projects or disrupt live AI services.
Think of it like someone sneaking into your supercomputer lab to secretly run their own massive cryptocurrency mining operations, or just flooding your expensive machines with so many irrelevant requests that your legitimate AI work grinds to a halt. It's not just an inconvenience, it's a huge financial drain and an operational hit, disrupting business continuity.
Definitely. And then there's unauthorized access to compute. This involves illicit use of the processing power, storage, or other infrastructure specifically dedicated to AI. An attacker who gains unauthorized access to these powerful systems could use them for their own malicious purposes, like running crypto mining operations to generate illicit revenue, as you said. Or more insidiously, to covertly access sensitive AI models and their underlying data for espionage or theft. They essentially hijack your multi-million-dollar AI infrastructure for their own ends.
Finally, within the development context, the source brings up threats on AI governance. These speak to broader systemic and ethical issues that are crucial to responsible AI development. First, lack of transparency.
Lack of transparency refers to the persistent challenge of black box models, where the decision-making process of the AI is opaque and cannot be easily understood or explained by humans. We know what goes in and what comes out, but the intermediate steps are a mystery.
We can't see inside the box.
Exactly. This makes it incredibly difficult to audit the AI's behavior or identify the source of biases, or even understand why it made a particular decision. This leads to significant trust issues, particularly in high-stakes applications like medical diagnosis or legal judgments.
So this means we can't fully peek behind the curtain of the AI's brain to understand its reasoning. If you can't see how it thinks, how can you truly trust its outputs, especially when those outputs have significant real-world impact? This also makes identifying and mitigating other threats like poisoning much harder, I imagine.
Precisely. Next, we consider bias and fairness. This discusses the critical risk of discriminatory outcomes being inherent in the AI model. These biases often stem from biased training data that reflects existing societal inequalities, or from flawed algorithms that inadvertently amplify those biases during learning. The concern here is that an AI system, if not carefully designed and audited for fairness, can perpetuate and even amplify existing societal inequalities, leading to profoundly unfair outcomes.
Like in hiring.
Exactly. An AI used for hiring might disproportionately filter out qualified candidates from underrepresented groups. If its training data contains historical hiring biases, it just learns the bad patterns. And lastly, under governance, we have regulatory noncompliance. This highlights the critical failure to adhere to legal standards and regulations throughout the AI development lifecycle. With increasing AI regulation emerging globally covering areas like data privacy, explainability, fairness, noncompliance can lead to severe financial penalties, significant legal action, and irreparable reputational damage. It's not just about technical security, it's about operating within the legal and ethical guardrails defined by society.
So what does this all mean for you listening? The development phase is clearly not just about building a functional AI. It's a critical juncture for baking in security, addressing ethical considerations like bias, and ensuring regulatory compliance from the ground up. It's a proactive approach, aiming to prevent problems rather than trying to fix them after deployment, which is often far more costly and complex, if not impossible.
That sums it up well.
Now that we've thoroughly explored development time threats, those vulnerabilities that can be baked into an AI system from its inception, let's pivot. Let's look at the second major category, runtime security threats. How do these fundamentally differ from the vulnerabilities we've been discussing that occurred during the AI's creation and training?
Well, these are distinct because they're primarily application security attacks due to security weaknesses that are not AI specific. But, and this is key, they are specifically leveraged against the AI solution once it's operational and deployed.
Okay, so not AI-specific weaknesses, but attacks targeting the AI.
Right. Think of it this way. These attacks often exploit vulnerabilities in the software wrappers or other IT infrastructure that host the AI, rather than necessarily altering the core AI algorithm itself at its deepest level. It's more about how the AI interacts with its broader IT environment, like the surrounding applications, networks, operating systems, user interfaces, and how those external systems can be exploited to compromise the AI's function.
So it's about exploiting the environment around the AI, but using that as a conduit to compromise the AI's function or extract information from it. And if we look at the OWASP-PIC Gen AI model, specifically figure 2.10 in the source, what's fascinating here is how traditional application security concerns are now directly applied to and often amplified by generative AI, creating new attack vectors. Let's dive into some of those runtime-specific threats listed. First, input prompt injection during runtime. We mentioned this before, but specifically at runtime now.
Yes, re-emphasizing this, input prompt injection is a key runtime attack. It's where malicious input from a user directly exploits a live running AI system, especially Gen AI. The goal is to subvert security safeguards, maybe bypass content filters, extract sensitive information like proprietary training data or internal instructions, or force the model to generate undesirable content, all through clever manipulation of the prompt itself. This is distinct from development time prompt injection, which corrupts the training. Here, the attacker is directly interacting with a live model.
This is often the most talked about AI attack in the news, isn't it? We hear about jailbreaking AI chatbots, or users finding clever ways to make the AI say or do things it definitely shouldn't, like generating harmful content or revealing its internal instructions, even when strict guardrails are supposed to be in place. It's a constant cat-and-mouse game where users continuously find new ways to bypass the AI's filters.
Precisely. Then there's model behavior at runtime. This refers to how attackers can manipulate the model's outputs or cause unexpected behavior once the AI is deployed and actively in use. This isn't about altering the core code or the training data. Rather, it involves subtly influencing its responses or classifications through interaction patterns or the real-time data it processes to achieve malicious ends.
Can you give an example?
Sure. By sending a high volume of specific types of queries, an attacker might subtly skew an AI's real-time recommendations or predictions to favor certain outcomes or products without ever directly injecting malicious code. It's manipulation through interaction.
So the AI itself might appear to be working normally, but its subtle behavioral changes or deviations from its intended output could have significant undesirable consequences in practice. It's a more nuanced form of manipulation than an outright crash or takeover.
Exactly. Another threat, which we've discussed in the development context, can also manifest critically at runtime: model poisoning.
Poisoning at runtime. How?
Well, if an AI system is designed to continuously learn and adapt from live incoming data or feedback loops, it can be poisoned at runtime through continuous malicious updates or manipulated feedback. This leads to a gradual degradation of the model's performance, accuracy, or ethical alignment over time as it incorporates bad data into its knowledge base. Unlike a one-off attack, this can be an ongoing, stealthy compromise.
That's a constant battle, isn't it? If your AI is always learning, you have to constantly ensure it's learning from a clean, untainted source in real time. This means data protection and integrity isn't a one-time setup during development. It's a constant, vigilant, operational effort. It requires sophisticated monitoring for anomalies throughout the AI's entire lifecycle.
Absolutely. And that leads directly to data confidentiality and integrity at runtime. There's an ongoing critical need to protect sensitive data processed by the AI in real time. This means ensuring it's not exposed data confidentiality and that it's not tampered with data integrity during its operational use. This applies both to the data processes like real-time customer queries or sensor data and any data it generates or stores, like personal profiles or system logs. Protecting data in transit and in memory becomes paramount.
This definitely reinforces that data protection isn't a single setup. It's a constant, vigilant effort throughout the AI's entire operational life, especially as sensitive information flows in and out of the system. It's like keeping a watchful eye on a valuable resource as it moves through various hands and processes in a bustling environment.
Well put. And finally, a re-emphasis on output prompt injection at runtime. This is where the AI itself generates malicious instructions or content as part of its normal output. This malicious output can then affect other systems or users interacting with it, potentially creating a dangerous chain reaction of vulnerabilities across an interconnected system.
Like the example you gave earlier, with malicious code in the output.
Exactly. A generative AI, when asked to write code, might be tricked into inserting a malicious API call that then triggers a vulnerability in a connected service. The AI becomes an unwitting participant in the attack, acting as a vector.
So it's not just about what goes into the AI that could be malicious, but what comes out of it, and how that output might then be weaponized or misused in subsequent actions. That's a crucial distinction for you, the listener, to grasp. The AI isn't simply a target. It can become an active conduit for further attacks.
A very important point.
Okay, moving on to the third broad type of threat listed in the source, separate from development and runtime vulnerabilities, we have AI solution disruption. This sounds like it could be quite broad and critically impactful to overall availability.
It is indeed. As AI solutions become more prevalent and increasingly integral to daily life and critical business processes, think of AI powering financial trading, energy grids, or emergency services. They become prime targets for denial of service or degradation attacks. The objective here is simply to make the AI system unavailable or unusable to its legitimate users,
How is that achieved?
usually by overwhelming the AI with a large volume of inferential requests or data loads or other forms of malicious activity that consume its computing resources, rendering it unable to respond or function effectively. It's essentially a digital flood designed to drown the AI's operational capacity.
So, what does this all mean for the real world? It means AI availability is as critical a security concern as its accuracy or fairness. If AI is powering a hospital's diagnostic tools, managing a city's traffic signals, or securing a nation's financial transactions, disrupting it could have severe real-world consequences, far beyond mere inconvenience. It moves from a theoretical vulnerability to a tangible threat to societal function.
Absolutely. Availability is key.
Okay. We've covered the unique and evolving landscape of AI threats. It's quite a lot. From those insidious vulnerabilities embedded during development to the more traditional yet amplified runtime attacks, and even those that seek to disrupt AI services entirely. Now, the big question, how do we defend against them? What's fascinating here is the source's emphasis on the continuing fundamental relevance of conventional security controls.
That's a crucial point the source makes very clearly, and it's often overlooked in the hype around AI's novelty. It asserts that conventional security controls remain important and are still applicable to AI-related threats. This means that the fundamental principles of good cybersecurity like robust authentication, meticulous network segmentation, prompt patch management, comprehensive incident response, strong encryption, they don't just disappear because AI is
All
involved.
the foundations.
Exactly. They form the foundational bedrock upon which AI-specific controls are built. You really can't secure AI effectively without first having a strong traditional security posture.
But these general controls aren't enough on their own for AI, right? There are AI-specific nuances, adaptations, and entirely new controls we need to consider. Let's talk about data, which is at the very heart of AI systems and a primary target of many threats we discussed.
Absolutely. One of the most important areas for AI-specific controls is applying robust measures to the training data itself, primarily to prevent data leakage and poisoning. This isn't just about storing it securely. It involves implementing rigorous data validation processes to ensure data quality and integrity before it's even used. It involves sanitization techniques to remove sensitive or malicious elements and meticulous version control for datasets. Furthermore, securing the storage environments for these crucial datasets with strong access controls and encryption is paramount. Compromised training data leads directly to a compromised AI.
So this is about ensuring the AI learns from a clean, secure, and untainted source right from the start.
Yeah.
It's that fundamental garbage in, garbage out principle, but with a critical security twist.
Right.
Ensuring the AI's foundational knowledge is unimpeachable and free from malicious corruption.
Exactly. Furthermore, the source highlights the imperative need to expand access controls, expand them beyond traditional IT systems to encompass the overall AI solution. This means carefully managing who has permission to access, modify, or interact with AI models, their underlying data, and their outputs at every single stage of the AI lifecycle, from initial data collection and model training to deployment, fine-tuning, and continuous operation. This extends to API access, model hosting environments, and even the inference endpoints where the AI makes predictions.
So it's not just about who can log into a server. It's about granular, role-based control over every single component and interaction point of the AI system, from the data scientists accessing raw training data to the MLOps engineers deploying the model, and even the end users interacting with its outputs. That's a significant departure from how we might typically secure traditional software systems. It demands a much more nuanced approach to permissions and privileges.
Indeed. And delving deeper into data, we must emphasize data confidentiality, minimization, and integrity controls. These are absolutely crucial to preserve the privacy of personal data within AI systems, especially given the vast amounts of sensitive data AI often consumes for training. The source explicitly states that encrypting the dataset may be necessary at various stages.
Even during training.
Well, auditors, for instance, would verify that while the training process might require data to be readable at certain points for processing, encryption for data at rest and in transit is applied rigorously wherever possible to protect sensitive information, both within the development pipeline and in the deployed environment. And data minimization only, collecting and retaining the data truly necessary, is another key control here.
This raises an important question for you, the listener, about balancing utility and security. How do you effectively train a powerful AI model, allowing it to learn from vast, often sensitive data sets, while simultaneously keeping that sensitive data secure, private, and compliant with evolving regulations? It's a delicate dance, isn't it? Between enabling AI's incredible power and ensuring its responsible and secure operation at every turn.
It truly is a delicate dance.
This deep dive into Chapter 2, Part F of the ISAC manual has truly illuminated the intricate and evolving web of threats unique to AI systems. We've seen them emerge at every stage, from subtle malicious injections that compromise the very foundation during development, to direct runtime disruptions and persistent data vulnerabilities that plague AI throughout its operational life.
And the crucial insight we've underscored throughout this deep dive, I think, is that while new transformative technologies like AI undeniably bring novel and complex risks, the core principles of security remain profoundly relevant. However, they must be adapted and expanded significantly to address the specific nuances of AI models, the vast and often sensitive data they consume, and the dynamic environments in which they operate. It truly represents a paradigm shift from simply securing IT systems to securing the very intelligence, the learning processes, and the decision-making capabilities of the system itself.
Absolutely. Reflecting on this journey, being truly well-informed in the AI space means not just appreciating AI's incredible capabilities,
Yeah.
but also understanding precisely where its vulnerabilities lie and the sophisticated multi-layered measures organizations are working on to protect against them. This knowledge empowers you to ask better questions, demand more secure AI solutions, and ultimately contribute to its responsible and resilient development and deployment.
And, if we connect this to the bigger picture, the rapid evolution of AI also means that the threats will continue to evolve, often at an accelerating pace. So, a final thought to ponder for you listening. As AI continues to integrate more deeply into society and becomes even more autonomous, maybe capable of self-modification, perhaps even reasoning, how might the very definition of control and threat evolve? And what new, perhaps even currently unimaginable technical and ethical challenges will emerge in securing these increasingly intelligent systems?
That's a powerful thought to leave you with. Thank you for joining us on this deep dive. Keep exploring, keep questioning, and we'll see you next time for another plunge into the fascinating, complex world of knowledge.